A randomized approximation algorithm for max 3 set. In the previous section, we saw a number of ways in which linearity of expectation can be used to analyze a randomized process. We now described an applications of this idea to the design of an approximation algorithm. The problem we consider is a variation of the 3-set problem, and we will see that one consequence of our randomized approximation algorithm is a surprisingly strong general statement about 3-set that on its surface seems to have nothing to do with either algorithms or randomization. The problem, when we studied NP-completeness, the core problem was 3-set, given a set of clauses C1, C2, C3 until Ck, each of length 3, over a set of variables x equals to the set x1, x2, x3, and so on to xn. Thus, there exists a satisfying truth assignment. Intuitively, we can imagine such a problem arising in a system that tries to decide the truth or falsehood of statements about the world, the variables, the set xi, given pieces of information that relate them to one another, the clauses, the set cj. Now the world is a fairly contradictory place, and if our system gathers enough information, it will end up with a set of clauses that has no satisfying truth assignment. What then? A natural approach, if we can't find a truth assignment that satisfies all clauses, is to turn the 3-set instance into an optimization problem, given the set of input clauses C1, C2, C3, and so on to Ck, find a truth assignment that satisfies as many as possible. We will call this the maximum 3 satisfiability problem, or max 3 set for sure. Of course, this is an NP-hard optimization problem, since it's NP-complete to decide whether the maximum number of simultaneously satisfiable clauses is equal to k. Let's see what can be said about the polynomial time approximation algorithms. Designing and analyzing the algorithm. A remarkably simple randomized algorithm turns out to give a strong performance guarantee for this problem. Suppose we set each variable x1, x2, x3, and so on to xn independently to 0 or 1 with a probability 1/2 each. What is the expected number of clauses satisfied by such a random assignment? Let z denote the random variable equal to the number of satisfied clauses. As in section 13.3, let's decompose z into a sum of random variables that each take the value 0 or 1. Specifically, let zi equals to 1 if the clause ci is satisfied, and 0 otherwise. Thus, z is equals to z1 plus z2 plus z3 and so on plus zk. Now the expectations of zi is equal to the probability that ci is satisfied, and this can be computed easily as follows. In order for ci not to be satisfied, each of its 3 variables must be assigned the value that fails to make it true. Since the variables are set independently, the probability of this is 1/2 to the third, which is equals to 1/8. Thus, clause ci is satisfied with probability 1 minus 1/8, which is equals to 7/8, and so the expectation of zi is equals to 7/8. Use the linearity of expectation, we see that the expected number of satisfied clauses is E of z is equals to E of z1 plus E of z2 and so on plus E of zk, which is equals to 7k divided by 8. Since no assignment can satisfy more than k clauses, we have the following guarantee. 13.14. Consider a 3-set formula where each clause has 3 different variables. The expected number of clauses satisfied by a random assignment is within an approximation factor 7/8 of optimal. But if we look at what really happened in the admittedly simple analysis of the random assignment, it's clear that something stronger is going on. For any random variable, there must be some point at which it assumes some value at least as large as its expectation. We've shown that for every instance of 3-set, A random truth assignment satisfies a 7/8 fraction of all clauses in expectation. So in particular, there must exist a truth assignment that satisfies a number of clauses that is at least as large as this expectation. 13.15 For every instance of 3 set, there is a truth assignment that satisfies at least a 7/8 fraction of all clauses. There is something genuinely surprising about the statement of 13.15. We have arrived at a non-obvious fact about 3 set, the existence of an assignment satisfying many clauses whose statement has nothing to do with randomization, but we have done so by a randomized construction, and in fact, the randomized construction provides what is quite possibly the simplest proof of 13.15. This is a fairly widespread principle in the area of combinatorics, namely that one can show the existence of some structure by showing that a random construction produces it with a positive probability. Constructions of this sort are said to be applications of the probabilistic method. Here is a cute but minor application of 13.15. Every instance of 3 set with at most 7 clauses is satisfiable. Why? If the instance has k which is less than or equals to 7 clauses, then 13.15 implies that there is an assignment satisfying at least 7k divided by 8 of them. But when k is less than or equals to 7, it follows that 7k divided by 8, which is greater than k minus 1. And since the number of clauses satisfied by this assignment must be an integer, it must be equal to k. In other words, all clauses are satisfied. Further analysis, waiting to find a good assignment. Suppose we are satisfied with a one-shot algorithm that produces a single assignment with a large number of satisfied clauses in expectation. Rather, we'd like a randomized algorithm whose expected running time is polynomially and that is guaranteed to output a truth assignment satisfying at least a 7/8 fraction of all clauses. A simple way to do this is to generate random truth assignments until one of them satisfies at least 7k divided by 8 clauses. We know that such an assignment exists by 13.15, but how long will it take until we find one by random trials? This is a natural place to apply the waiting time bound we derived in 13.7. If we can show that the probability of random assignment satisfied at least 7k divided by 8 clauses is at least p, then the expected number of trials performed by the algorithm is 1 divided by p. So in particular, we'd like to show that this quantity p is at least as large as an inverse polynomial in n and k. For j equals to 0, 1, 2, 3, and so on until k, let pj denote the probability that a random assignment satisfies exactly j clauses. So the expected number of clauses satisfied by the definition of expectation is equal to the summations of j times pj, summing for all j starting with j equals to 0 to k to j equals to k, and by the previous analysis, this is equals to 7k divided by 8. We are interested in the quantity p equals to the summations of pj, summing for all j which is greater than or equals to 7k divided by 8. How can we use the lower bound on the expected value to give a lower bound on this quantity? We start by writing 7k divided by 8 is equals to the summations of j times pj, summing with index j starting from 0 to k, which is equals to, if we divided the range of the ranges of j into two parts. The first part is the summations of j times pj, summing for all j which is less than 7k divided by 8. The second part is the summations of j times pj, summing for all j which is greater than or equals to 7k divided by 8. Now let k prime denote the largest natural number that is strictly smaller than 7k divided by 8. The right-hand side of the above equation only increases if we replace the terms in the first sum by k prime times pj and the terms in the second sum by k times pj. We also observe that the summations of pj summing for all j which is less than 7k divided by 8 is equals to 1 minus p, and so 7k divided by 8 is less than equals to the summations of k prime times pj summing for all j which is less than 7k divided by 8 plus the summations of k times pj summing for all j which is greater than or equals to 7k divided by 8, which is equals to k prime times 1 minus p plus k times p, which is less than or equals to k prime plus kp, and hence kp is greater than or equals to 7k divided by 8 minus k prime. But 7k divided by 8 minus k prime is greater than or equals to 1/8, since k prime is a natural number strictly smaller than 7/8 times another natural number, and so p is greater than or equals to 7k divided by 8 minus k prime, then divided by k, which is greater than or equals to 1 divided by 8k. This was our goal, to get a lower bound on p, and so by the waiting time bound 13.7, we see that the expected number of trials needed to find the satisfying assignment we want is at most 8k. 13.16. There is a randomized algorithm with polynomially expected running time that is guaranteed to produce a truth assignment satisfying at least a 7/8 fraction of all clauses.